Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. Microphones come in many shapes and sizes beyond the examples we've seen so far intended for laboratory or research and development use. In this video, we'll be introduced to the wide variety of microphones that are optimized for distinct applications.
So let's get started. If someone said the term microphone, you might get an image in your head like the microphone that's shown here in the photo. This is called a cardioid microphone. It's a specialized microphone that's specifically used for live performances and recording environments. The term cardioid comes from mathematics. A cardioid is a curve traced by a point on the perimeter of a circle when that circle rolls around another fixed circle of the same radius. We see a cardioid here traced out in the red color in the animation. The microphone picks up sound where it points, but not behind it. This is due to the fact that the microphone is positioned in such a way that there are interference passages behind the main diaphragm. So when sound is incident from the front side of the microphone, it constructively interferes. When sound is incident from the side or the back of the microphone, it destructively interferes. So this helps in practice to suppress crowd noise and background noise in recordings. Cardioid microphones are the common variant of microphone we might see day to day. Sometimes these are called cardioid condenser microphones, and they're widely available for desktop use, such as the Blue mics and so on. Here is our cardioid microphone. This is made by Behringer. The model is an Ultra Voice XM8500. It uses an XLR cable for communication to an amplifying board, and here is our grill and windscreen. This grill has a foam lining inside to minimize the influence of fluid flow, like wind, that otherwise creates noise. We can take this part off. Here's our microphone. Behind this 1-inch opening is a diaphragm. The foam is held down to prevent me from pulling it off without damaging the diaphragm. There's a metal backing behind the foam also to prevent damage. You can feel it as you depress on this. The microphone is lined with these additional sides that have partial felt covering and an additional chamber on the back side. All of these passages allow interference so that the cardioid pattern can be amplified. Boom microphones, or sometimes called shotgun microphones, use a principle that's derived from the cardioid. Rather than a single interference passageway, a boom microphone or shotgun microphone uses a multitude of these interference passages. As a result, the microphone truly only hears what's ahead of it and significantly suppresses sound that's arriving from other angles of incidence. There's still only one microphone in the boom. It's the design and the shape of the boom itself that helps create the directionality of the mic. Here is our boom or shotgun microphone. The windscreen is also quite large to cover the entire interference tube. A protective metallic grill is on the front as well, in case the microphone is dropped. The interference tube has these openings all along the extent of the tube. And the microphone is positioned in this area on the transducer. This is a powered microphone, which allows you to control the filtering, gain, as well as turn it on and off. When we hear sounds arriving from long distances, they effectively arrive at our ears as plane waves, like we've learned before regarding the acoustic far field. Plane waves may be focused by parabolas, and specifically by parabolic reflectors. Parabolic microphones use this principle, especially in sporting environments, where we want to have high quality sound, for instance, a quarterback calling a hike, but this sound is recorded at a very long distance. So a parabola focuses those acoustic plane waves to a point. and then the microphone is placed at the center of the parabola. This characteristic of sound is analogous to optics. We'll learn more about this principle of geometric acoustics, but this is the first time we see evidence of it. For cell phones, MEMS microphones are used. The principle is similar to that of a condenser, but the microphone is fabricated on a much smaller length scale. They are etched from silicon wafers and then deposited with a multitude of conductive materials at different layers. A diaphragm is suspended over a backplate, and the charge and voltage differences that are created through motion of the diaphragm with respect to the backplate leads to a converted acoustic pressure. They use the condenser technology, but not necessarily the electric principle of prepolarization. We see MEMS microphones everywhere nowadays in small-scale electronics. They have much greater dynamic range for their size than conventional condenser microphones, which warrants their widespread use for cell phone communication. Dynamic range might even approach 100 decibels, which is significant. So let's summarize what we've learned. Many microphones are available that are optimized for certain listening environments. Studio recordings or live sound amplification will use cardioid or shotgun microphones. Laboratory settings use the more conventional electric condensers that we've seen already.
That's it for this video. In the next video, we'll learn more about audiological transduction in terms of loudspeakers as well as hearing assistive solutions.